Alrighty, welcome back. We are looking at discrete random variables today, exercise 13C. Um, First of all, they've got a bit of an example here where they're talking that they've got three balls being drawn at random from a jar containing 4 white and 6 black. In this particular case, the note it says with replacement. If you had to write out the sample space, it could be listed here as all the different possibilities of what could be drawn when we draw 3 at random. So here are all the possibilities of the combinations for white and black. Now, in this particular case, it says if x represents the number of white balls in this sample space, the possible values of x are 0, 1, 2, or 3. That is, they're saying you could, in this experiment, draw 0 white out of the 3, 1 white out of the 3, 2 white out of 3, or 3 of them could be white out of the 3. It says here, since the actual value of x will take is the result of the random experiment, we can say that x is the random variable. So that's listed there. A random variable is a function that assigns a number to each outcome in the sample space. Now, what you should know is that a random variable can be either discrete or continuous, and we've spoken about discrete random variables before, where it can take on only a countable number of values. Some examples that they've said here is it could be the number of white balls in the sample space, which is can be counted. You can count it with either 1, 2, or 3. Other examples you can count as well as number of children in a family. And also a person's shoe size. It says here, note that discrete random variables do not have to take on a whole number value. On the other hand, you can have a continuous random variable, and it's one where, or is one that can take on any value in an interval of a real number line, and is usually, but not always, generated by measuring. So as soon as you hear of height, weight, and the time taken to complete a puzzle, for example, they're all continuous random variables, and you note that they can all be measured. So they're continuous random variables. So what we're going to start doing as well as we spoke about at the start, as we said, you're going to consider the sample space for each of these random experiments. In the one we spoke about, the sample space associated with the value of x. So here with the outcomes in the sample space, you can see x represents how many were white in each of those scenarios. So here there were none. This one there's 1, 1, etc., etc. White, white, white. There's 3 here. So that can be done. So let's have a look at an example. It says here a jar contains 4 white and 6 black balls. What is the probability that if 3 balls are drawn at random from the jar, again with replacement, so it goes back in after each one, a white ball will be drawn exactly once. And so when we're talking about a white ball being drawn exactly once, we're talking where x is equal to 1 in that table above. So where x equals 1, so that it's only one white being drawn, those possible outcomes were in these scenarios here, where you could have white, black, black, the black, white, black, and also the black, black, white scenarios. It also goes on and says, since there are 10 balls in total, the probability of getting a white was 4 out of 10, because there were 10 obviously in total, so 0.4, and the probability of getting the black, there was 6 out of the 10 in total, so it's 0.6. So to actually go ahead and calculate the probability of x being equal to 1, so in this particular scenario with the discrete random variable, we calculate the probability of this here, white, black, black. So obviously we're multiplying these through. The white's 0.4 by 0.6 by 0.6. It's probability of that one. Probability of black, white, black, it's 0.6 by 0.4 by 0.6. And black, black, white is 0.6 multiplied by 0.6 multiplied by 0.4. Once we've got each of those probabilities, we add those together and we get this here as being 0.432. Perfect. So we can go on and we can get what's called discrete probability distributions. It says here the probability distribution for a discrete random variable consists of all of the values that a random variable can take together with the probability of each of those values. So again, the scenario they've drawn up is using a dice, or the die, sorry, and it's a fair one, so you'd expect it to be equal. So the numbers 1 to 6 on the die, probability of each of those events occurring is 1/6. So again, it says the probability distribution of discrete random variable x is described by a function as listed here. When it's listed like that, that function is called a discrete probability function, or can also be known as a probability mass function. So again, if we think about what was above with the black and white balls, so example number 11, the probability distribution for x, that is the number of white balls in the sample, is given by the following table. So again, we just worked out here where the probability was 1, so there was 1 as white, and you can see here in that table the calculation was 0.432. If you did the same sort of thing we did above, but for 0 white, 2 white, or 3 white, this is how the table would be filled out. Again, it can be shown in a table, the discrete probability function, or you can also be showing it using a graph as shown here. Another thing that you should note is that the probabilities in the table all add together to 1. Yep. And that must occur if all the values of the random variables have been listed. Perfect. Some other things that we're going to be looking at as well is there's some notation. So it says the sum of all the values p of x is written using the sum of symbol here, and if you are going to get the sum of all the values of p of x but between some different values such as a and b, it's listed with the sum symbol between those two values a and b as such. So that's just listed there, and we spoke about this one here. Yep, if you're going to find it between including the values a and b. Yep, so it actually includes those on either side as well. Let's have a look here. This is it says here, consider the table shown. This is worked example number 12. It says, does this meet the conditions to be a discrete probability distribution? So again, there's a few things that we need to know. So first of all, each of these values of p of x has to be between 0 and 1 as a probability, and so it is indeed meet that condition. And the other condition is that all those values have to add together to make 1. And indeed, when you add those together, it does add up to 1. So this does meet the condition of discrete probability distribution. It then goes on saying, use the table to find the probability of x being less than or equal to 2. So again, when you're looking at this table, to find the probability when x is less than or equal to 2, you're looking at all of the values or the probabilities that are 2 and below. So we're going to add these all together. So the probability of obviously p of 0 was 0.2, here is 0.3, here is 0.1. Adding those together, and we get the probability of x being less than or equal to 2 is 0.6. So if you've got the table, it should be pretty easy to get this happening. Next example, it says here, worked example number 13. It says, let x be the number of heads showing when a fair coin is tossed 3 times. So again, good to get in the habit of listing out the sample space, so you can see all of the possibilities. From there as well, it says find the probability distribution of x and show that all the possibilities add together to make 1. So again, finding p of 0 when there are 0 heads being shown. The only time that there's 0 heads being shown is when they're all tails, so tails, tails, tails. That is 1 possibility out of all of the 8. Going ahead and finding the probability that there is 1 head. So looking for where there's 1 head, there's 1 head here, 1 head here, and 1 head here. They are each worth, or each probability is 1/8. Adding them together, we get 3 out of 8. We can do that for each of those scenarios that are listed there. Again, you want to make sure that all the probabilities add together to make 1. Once we've found each of these here, that plus that plus that plus that, that does equal 1. So we are all good there. Next it's saying, hey, find the probability that 1 or more heads show. So in this particular case, we've put this data into the probability distribution table. To find the probability that 1 or more heads is shown, here is 1 head shown. and more is obviously has to be greater than that. So we are looking at P of 1, P of 2, P of 3. We're going to add those probabilities together. We get 7 out of 8. This one here, part C, was saying find the probability that more than one head shows. So in this particular case, more than one head means it has to be greater than 1, not equal to 1, just greater than 1. Not greater than or equal to, but greater than 1. So that leaves just these here when it's 2 and when it's 3. So again, working out these probabilities, adding them together, we've got 4/8, which is the same as 1/2. Example number 14, we're powering through. Excellent. It says here the random variable x represents the number of chocolate chips in a certain brand of biscuit. Biscuit. Delicious. And it is known to have the following probability distribution here. Excellent. They've already run that calculation for us. So when they ask us to find each of these, it's just a matter of utilizing this table. So it says here, find the probability that x is greater than or equal to 4. So again, in this case, here's 4. It's going to include that and the things that are larger. We add each of those probabilities together. When it's 4, when it's 5, when it's 6, and when it's 7. Adding those together, 0.74. Next one here is saying probability that x is greater than or equal to 4 given that x is greater than 2. So again, we need to go back to the previous exercise where we looked at the conditional sort of scenarios with conditional probability. And in this particular case, utilizing that rule, when you are finding this out, it's going to be obviously the intersection of both of these divided by the probability of what's given. Yep. So the intersection of these is, in this particular case, where it's greater than or equal to 4, and then that is divided by this part here, where x is greater than 2. So once you have these here, you can run the calculation. Yep. Now, note the way that they've done this here as well, with the probability of x being greater than 2. Here, where you've got the probability of x being greater than 2, it's all of these things over here. You could add them all together, or another way is just saying, okay, 1 take away this one gives you what's remaining. So you need to think about this a little bit. And that can be obviously simplified down to 74 over 99. Next one, x being less than 5 given that x is greater than 2. So again, on the top, it's the intersection of both of those. So the intersection of both of those is the values that are greater than 2, but also less than 5, divided by what's given here, which is x being greater than 2. So again, if we think about these things here, finding out the probability of the values between 2 and 5, but not including them. So between 2 and 5, the things that are there but not including them are when it's 3 and when it's 4. So we can get those probabilities. And that's divided by, obviously, the probability of x being greater than 2, which we worked out up here anyway. That's 0.65 divided by 0.99. We can simplify that down to 65 over 99. So have a little bit of a think about those ones. Cool. Here is the summary for this particular exercise. Again, please note the things that we spoke about and enjoy this exercise. Bye for now.